course. In this lecture, that we will understand what is Lamport clock. So, in the previous part of this video, we understood what is time, how time is synchronized using NTP, network time protocol. Also, that how time affects how time plays a role in distributed systems. We saw that we cannot rely on timestamps on ordering of the messages in the distributed systems. So in this lecture that we will learn Lamport clock and how it is used in distributed systems to define a partial ordering of the data and message. Here is our Lamport clock. So Lamport clock is a clock which is nothing but a logical clock. So far we've seen what is physical clock, time that is based on the CPU clock, time that is based on epoch clock, which means a clock that starts from January 1, 1970. This is logical clock, and it is based on counter. Another clock is a physical clock. We already see this one. Physical clock is based on and CPU clock, CPU, and another one is a epoch time. January, since January 1, 1970. From this onwards, that we will measure the time. The clock starts from this time. So whatever the time we use in our system is a physical clock. So logical clock is based on the counter. We will see how it is used. Before that, Lamport clock is an algorithm to define message ordering in a distributed system. So whenever we will see the algorithm of Lamport clock. First, we will see for each node it has counter that's called T0. So for each case, whenever there is an event occur on a local machine, we have to increment T equal to T plus. There is an event occur to send message to other node. We will increment the clock count, which means the counter count, and we will send the timestamp associated with the message. Here we send the message with the timestamp to the other nodes. So these algorithm for the Lamport clock. For example, here we are going to see an example of the diagrams. So we have four machines. One is in this example, we have four machines connected. This is called simple distributed systems, and this is called simple distributed systems. So client sends the message to this machine. Let's call each machine. This is an S1 with the counter 0. This is an S2 and with the counter 0. Initial counter is 0. So each machine has its own counter for Lamport clock. So it initializes with the 0. The machine is 3 and it has 0. Here is 4 and it is counter 0. So client then sends message M, which is sent to this machine. Now this message has to be sent to all those machines, but we will see how the Lamport clock works. We already seen that timestamp we cannot rely on timestamps. We seen why is that. Here we will see how the message is transferred and how the Lamport clock is used. We seen that Lamport clock is 0 here. Lamport clock is initialized with 0, right? So here the message comes. So the counter is implemented to 1. Now the counter is 1 because it receives a message. Then again, the message comes, and now The counter is incremented with 1. It receives a message. Then it sends a message to the other two nodes. Now then again it increments the counter 2 and sends this message into this node. Upon receiving this message, it will check with the current Lamport of this SS2. So it is 2 is greater than 0. So here it will store as 3 m. So here upon receiving the message in Lamport Clock algorithm, here one more thing you have to add. Upon receiving the message event and receiving the message, it will increment the counter and increment the counter. How do you increment the counter? It will get the max of the received. For example, it received some clock T1 and we have a current clock and received clock. So it will get the max of it and plus 1 you get the current timestamp. Let's say it's T hash. Then this one is used to persist this message and store the message along with this clock. So T comma IM here. So this is how the current clock is here as 0 and the receipt clock is at 2 and max of it and plus 1 and store it with the message. So this is how the Lamport clock works. Now we have the counter here 3. Here again it will send 3 comma IM. It increments the counter and sends the message again. Upon receiving this message will be stored here as 4 comma IM. Now this one send the message to here, right? So let's see it's 0.3. It's a 4 comma IM. So we see that there are multiple events happened in this structure, this distributed system architecture. Each event A happened here, then event B happened here, which means that when it sends a message, when it persists the message here, for example here it's persisted as 1 comma m, and it sends the clock becomes s1 equal to 3. Now 3 comes here, it will become 4 comma m. So the message, if you look at that, how the data is stored here, 1 comma m, then here 3 comma m, 4 comma m, and 4. So whenever the event receives, whenever the counter, it will increment the counter for any local event and it will send the message with the counter. On receiving, it will receive the counter and increment it and update the local counter. For example, here 3, here 4, here 4. Here we updated the counter and this is the message. So this is how the Lamport clock works. So why you have to use a Lamport clock when you use a timestamp? Because of ordering. So let's see what is ordering. You have to see the two important things here: partial order and total order. So what is partial order? We send the message from this machine to this machine. If the event A happened before event B, this is an ordering. I mean, this is a casual order. This is what called partial order. Since if you use a timestamp instead of counter, this will see, for example, here 1 comma m is lesser than 3 comma m, which means that the message that is stored in these machines, this is lesser than this one. We can say that this event happened before this one. So this ordering is partial ordering. So but we cannot use this timestamp. The reason timestamps are not reliable because when it synchronizes with the NTP, there may be a drift or NTP stepping that may cause incorrect clock. Or the computer when we set the incorrect clock. So that's why it's not completely on timestamp. Hello. What is partial order? So here one more change. So when the message is sent from this machine, the counter becomes 4 and it will be 4 comma m, and here it will be 5 comma m. So it was a little bit of mistake, and here the updated counter is 5. So we have 4 nodes that are connected, and we can add one more node, and just for the understanding that we can add one more node here, and the message that is sent from this node to this node, it will increment the 4 and it will be 5 comma m. On receiving it will be 6. It will be 6 comma m. So we have multiple nodes that are connected. So this is we are sending a message from one node to other nodes. So upon receiving the node or any local event, it increments one counter. On sending and receiving the message, it increments a counter and persists this with the message. So is there any possibility that these two counters can be same? It's possible. It's possible that since each machine has its own counter, so in some cases these counters may be same. For example, it could be 5 5. In those cases that we know that this event happened before this event and this event happened before this event, but we cannot say when the counters are same this event happened before this event. So partial ordering cannot be achieved with when the two nodes have the same counter, for example, same timestamp 4 comma m 4 comma m. In those cases, that what we can do is that, so it cannot be done with the Lamport clock. Also, we can do is with a vector clock. So we'll see in the next section how to do it in vector clock. Before that, we will see what is a total order. Total order is when the message is sent one node to other node, we can say that which event happened before the other event occurred across all the nodes. That's what total order is. Not just for between two machines. That's what's called partial order. But across all those machines for the message, we can say this is a total order. So how to do it? Let's say that we have persisted all those messages. We have 1 comma m, and then it happened 3 comma m, then 4 comma m. But this 4 comma m, this 4 comma m, this 4, let's say that this one is 1 comma, this is 3, and this one is 5. But this 4 comma m caused by this event, event from this machine. So it should be 1 comma m and 4 comma, and finally 6. So this is the ordering that happened in this distributed system example when the message is sent from one node to other node with the Lamport clock. So in order to achieve the total order, we can add 2 more variables, 2 more parameters, just like a node ID. We can give an individual node ID to each machines, and so we can uniquely identify the message across machines. So that, and we can add timestamp. So whenever we persist these two things with the message, we can uniquely identify the message, and we can able to order. And we can able to come up with a total order with these 2 extra parameters. So this is what is called total order. We can uniquely identify the message if we add those 2 things with the message, because there may be cases where 2 machines have the same counter for the message. We can use these things to find out the total logarithm of messages. So in the next section, we will see Lamport vector clock. So we see in that event A causes event B. So is it causal? It's a partial order, but we cannot say whether the two events are concurrent. For example, here this is 3, m and this is 4, m. So whether this event causes this event? No, this event didn't cause this event. So we can say this event are concurrent. But with the Lamport clock, we cannot able to identify that. So, but with vector clock, we can able to identify. Vector clock is a similar algorithm, except the counter, it maintains the vector of counter. We will see in the next section.